Hey guys, we're continuing on Unit 3. This topic is on the electromagnetic spectrum. So we first need to know about different categories of electrons. We have core electrons that are located on the inner energy shells, and then we have valence electrons, which are on the outermost energy shell. So here's an example. How many core electrons are in this element? How many valence electrons are in this element? So my valence electrons are the outermost electrons. So I would have 4. Then it says how many core electrons. So the core electrons are just anything else that's not a valence. So I would have 2 core electrons. Those are in green. What element is this? I know that this is carbon because I have 6 protons and 6 electrons. Here's another example. I would have 5 valence electrons. Those are shown in blue. And now remember, core electrons are just every other electron that's not valence. So I would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 core electrons. I know that this element is phosphorus because I have 15 protons and 15 electrons as well. So here's a picture of what electrons would look like just changing energy levels or shells. When they go from an outer ring to an inner ring, they lose energy, and we say that the electron is returning to its ground state. When they go the opposite direction from the nucleus out towards the outer rings, electrons are becoming excited. That causes them to gain energy. When electrons move back down to their ground energy level and they lose that energy, they release the energy in the form of a photon. So that's what we can actually see is the light and the color of the light. A photon is a tiny particle of light, and we measure that in wavelengths. Different wavelengths carry different amounts of energy. The color of the light depends on its wavelength. Visible light is a form of electromagnetic radiation. It travels through space as waves and as particles. So a wavelength has that weird little symbol that's called a lambda. That's the distance from crest to crest of a wave. The frequency is how many wave cycles per second, and it's measured in hertz. And then finally, amplitude is the crest to the trough. So the very top of the wave all the way to the bottom of the wave. Here's what a wavelength would look like, a wave cycle, I should say. So my top sections are the crests. When I'm measuring crest to crest, that's wavelength. The bottom section is a trough. When I measure crest to trough, it's called amplitude. This entire thing, however many of those I have in 1 second, that gives me the frequency. So I know everyone's heard of Roy G. Biv throughout grade school. The electromagnetic spectrum is arranged the same way in that rainbow pattern. So if you notice more towards the red side, you have bigger wavelengths or longer wavelengths, and then as you go towards purple, you have shorter wavelengths, but a higher frequency. So your energy will increase as you go towards those purple colors. On the red, orange, yellow side, you have a longer wavelength, a lower frequency, and a lower energy. On the blue, indigo, violet side, let's wait for that bell. On the blue, indigo, violet side, you have a shorter wavelength, but a higher frequency and a higher energy. Atomic spectra. So each element has its own unique line spectrum, which results when a photon is emitted. So each element has this, and it's basically like a fingerprint. It's unique for that element. These unique line spectra allow us to identify unknown substances, so we can guess what the element is based on what colors it emits. Okay, here's an example of what that looks like. So lithium releases some purples and a few greens and blues and a yellow and a red. That's its line spectra. So there's a line spectra for all of those elements. We can also calculate wavelength, frequency, and energy and do a little bit of math to find these things. So let's look at that. We have to know the speed of light, and we say it's in a vacuum. That just means there's no outside forces, there's no wind, there's no gravity, nothing like that. It's almost like a perfect situation. Next, oh, there we go. So my speed of light is a constant number, meaning it will always be this number. It's always going to be 3 times 10 to the 8th meters per second. So speed of light equals wavelength times frequency. That's the equation I'm going to use. And then you also need to know 1 nanometer is 10 to the 9 meters. So here's my equation. Speed of light, which is c, equals wavelength times frequency. You can also plug it into this triangle like we did with density. It works the same way, so we can divide or multiply based on what we're trying to find. Let's do an example. So you broke your arm. The x-ray they took of your arm uses waves that have a length of 2.19 times 10 to the 10 meters. What is the frequency of the x-ray? So I'm going to switch over to my notes so I can write. Let's see. There we go. Okay, so first thing I'm going to do is draw my triangle. We know speed of light because that's always the same. And we know, let's see, we're looking for frequency. We know wavelength is 2.19 times 10 to the 10. So this horizontal line tells me to divide. So I can just say 3 times 10 to the 8th divided by 2.19 times 10 to the 10. When you do that, you should get this answer, 1.36 times 10 to the 18. It can be in scientific notation. Oh, nope, I definitely wrote the wrong number there, sorry. Times 10 to the negative 2. Since this is frequency, my unit of measurement is a hertz, Hz. That's my answer for that one. Let's look at the next one. A laser emits light at a frequency of 4.74 times 10 to the 14 hertz. What is the wavelength of this light in nanometers? So normally wavelength is found in meters. This one wants it to be in nanometers, so we'll have to convert here in a second. So again, I can draw my triangle just as a reminder. I know speed of light, that never changes. I'm trying to find wavelength. And I know frequency is 4.74 times 10 to the 14. So again, I can divide 3 times 10 to the 8 divided by 4.74 times 10 to the 14. So when I put this in a calculator, I would make sure to keep these in parentheses so your calculator doesn't get confused. When you do that, you would get this number. So one important thing to note, and let me just say this is in meters, but our question wants it in nanometers. One important thing to note is when you're finding wavelength and it's in meters, it will always be something times 10 to the negative 7. It will always be that if it's meters. If I'm converting it to nanometers, it's just going to be 633 nanometers. So it's a really easy conversion. You can get rid of the decimal and you can get rid of the times 10 to the negative 7. So this is my answer. Okay, let's continue on. You can also find energy, and we say it's energy of a photon. It's the difference in energy between two energy levels. We use H, which is Planck's constant, and that number is 6.626 times 10 to the negative 34. So it will always be that number. The equation is energy equals H, Planck's constant, times frequency. Energy is also calculated in joules, so that would be your unit. We can use that triangle just like we did in the last problems, and I'll show you that in just a second. So here's an example. A certain electromagnetic wave has a length of 625 nanometers. What's the frequency? What's the energy? So let's go back over here. Oops. Okay, So I can use this again and say energy, Planck's constant, and frequency. But we don't know frequency, so we need to do 2 steps to this problem. The first step would be finding the frequency. So I have speed of light, which is what we were just doing a second ago. I'm looking for frequency, but they give me the wavelength. They say it's 625 nanometers. I need that to be in meters, so I'm going to say 6.25 times 10 to the negative 7. That would be meters. Anytime it's in meters, it's going to have that 10 to the negative 7. So my first step would be to divide these. Once you divide those, you should get something like this. That's frequency, so it would be in hertz. Okay, so now it's asking for energy in my question. So I need to go back and find energy. If I use that triangle, it could look like this. Energy, Planck's constant, which is 6.626 times 10 to the negative 34. My frequency that I just found, 4.8 times 10 to the 14th. And now, since those are side by side, I can multiply. Again, I would make sure that these are in parentheses so that it does not confuse your calculator. Okay, when I multiplied those, I got 3.18 times 10 to the negative 19. Since this is energy, my unit is joules. Okay. There are a few more examples. You can try that on your own.